Imagine, if you will, that we have two groups which we will creatively call Group 1 and Group 2. How would you compare these two groups? That is, how would you determine how similar or different they are from each other? And what do we mean by similar? What features of groups are we even using to compare them? To answer these questions and more, we will use a tool called a homomorphism. Consider the group of integers z and the integers mod 2. The operation we'll use in both groups is addition. The integers are an infinite group, while the integers mod 2 is a finite group with only 2 elements. So at first you might think these two groups are completely different from each other. But consider this. The integers can be broken into two sets, the even and odd integers. If you add one even integer with another, you get an even integer. If you add an even and an odd, you get an odd. If you add an odd and an even, you get an odd. And finally, if you add two odds, you get an even integer. Now compare this with the integers mod 2. In this group, 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. And 1 plus 1 equals 0. Do you notice a similarity? If you replace even with 0 and odd with 1, then these say the exact same thing. This is an interesting observation. By splitting the integers into two sets, evens and odds, we see these two sets behaved exactly the same as a group of integers mod 2. We can express this observation in mathematical terms by defining a function f from the integers to the integers mod 2. The function is simple. If an integer is even, map it to 0. If an integer is odd, send it to 1. Is it possible to create a reverse function that encodes our observation that evens and odds behave like the group of integers mod 2? The answer is no. Suppose we try to create a function g from the integers mod 2 to the integers. We'll send 0 mod 2 to some integer x and 1 mod 2 to some integer y. Since 0 plus 0 equals 0 mod 2, we want x plus x equals x in the integers. This is because if we are comparing groups, then the behavior of elements in the output should be similar to the behavior of the inputs. Solving the equation x plus x equals x gives us x equals 0. So g maps 0 mod 2 to 0. Next, 1 plus 1 equals 0 mod 2, so we want y plus y equals 0 in the integers. Again, this is because we want the inputs and outputs to behave similarly. If we solve y plus y equals 0, we get y equals 0. So g also maps 1 mod 2 to 0. The function g is rather trivial. It sends everything in the integers mod 2 to 0. In this direction, we lose the group similarity between the evens and odds and the integers mod 2. Keep this in mind when using a function to compare two groups. The direction can matter. Let's see another example where we take two groups and compare them for similarities. The integers mod 4 with addition as a group operation, and the group of four numbers, 1, -1, I, and -I, with multiplication as the operation. To compare them, let's look at the Cayley table for both groups. First, the group of integers mod 4 with the operation of addition. The way you say this aloud is the group of integers mod 4 under addition. This is the jargon used in math for specifying the group operation. In the upper left corner, write the group operation. Then, in the first row and first column, list all the elements in the group. Next, we go through and compute all possible 16 operations. 0 plus 0 equals 0 mod 4. 0 plus 1 equals 1 mod 4. 0 plus 2 equals 2 mod 4. 0 plus 3 equals 3 mod 4. Continuing, 1 plus 0 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, and 1 plus 3 equals 0. And we'll just go ahead and fill out the remaining 8 squares. Next, let's make the Cayley table for the numbers 1, -1, I, and -I under multiplication. To finish, we quickly perform the 16 multiplications. We now have the Cayley tables for these two groups. They're both the same size. They each have 4 elements. But do they behave similarly? Or are they different and unrelated from each other? We'll answer this question visually by coloring the squares. Each group has an identity element. For the integers mod 4, it's the number 0. And for the second group, it's the number 1. Let's highlight the identity elements red. To help you see the pattern, let's switch -1 and I in the group on the right. The red squares now form a similar pattern in both Cayley tables. Let's move on to the next element in the group of integers mod 4, the number 1. We'll go through and color all squares containing a 1 green. We do the same thing to the group on the right. The next uncolored element is I, so let's highlight all squares with an I green. Notice the pattern of green in both tables is the same. Let's keep moving. In the integers mod 4, highlight all the 2's blue. And in the next group, highlight the -1's blue. Once more, the blue pattern on the left is the same as the blue pattern on the right. And we'll fill in the squares with the last number using purple. Same pattern again. By coloring the squares a different color for each element, we can clearly see the patterns for both Cayley tables are exactly the same. They're identical groups. They just use different elements and a different operation, but other than that, the groups are equivalent. In both groups, if you combine a green element with a blue element, you get a purple element. Similarly, a blue combined with a blue gives you a red, and so on. Any such statement about one table applies to the other. We say these two groups are isomorphic, which means equal form. Now that we've seen a couple of examples, let's talk about things more generally. Suppose we have two groups, G and H. They can be any kinds of groups: finite, infinite, commutative, non-commutative, you name it. Now pick any two elements X and Y in the group G. If we combine X and Y, we get a third element in G. We'll pronounce this X times Y, even though the operation can be something completely different than multiplication. For the groups G and H to have similar group behavior, X, Y, and X times Y in G must correspond to the elements in the group H. The mathematical way to write down this correspondence is with a function. So we want a function f from G to H that sends this part of the multiplication table for G to a similar part of the multiplication table for H. F sends x to f of x, y to f of y, and x times y to f of x times y. Here's the critical observation. In the table for H, this square must also contain f of x times f of y. In other words, f of x times f of y must equal f of x times y. This type of function is the mathematical tool we use to compare two groups. We now have a tool for comparing two groups G and H. It is any function f from a group G to a group H, such that f of x times y equals f of x times f of y. We call f a group homomorphism, or just a homomorphism for short. One thing to be careful about is the operation on the left is the group operation in G, while on the right is the group operation in H. As an example, define the function f from the integer z to itself by f of x equals 2x. In this example, the group operation is regular addition. To check if it's a homomorphism, we only have to show that f of x plus y equals f of x plus f of y. From the definition of f of x plus y equals 2 times x plus y. And on the right-hand side, f of x equals 2x, and f of y equals 2y. 2 times x plus y does equal 2x plus 2y, so f is a homomorphism. Notice that the output of f is a set of even integers. The even integers are a subgroup of the integers. We'll explore this and other properties of homomorphisms later. After groups, the idea of a homomorphism is quite possibly the most important concept in abstract algebra. It allows us to connect similar groups and identical groups. Homomorphisms are also an essential tool for identifying the fundamental building blocks of groups. And as we move forward through abstract algebra, this idea will recur again and again. We will introduce a new object, rings, fields, vector spaces, and then define homomorphisms between them. The set of people who support us on Patreon is a finite but important group. They are homomorphic to the MdeG group. This famous group is something I just made up as a way to encourage you to support us financially on Patreon.